Physics fans, bit of background noise today, apologies for that, but I just figured it was so important to get this little video done since so many people are asking about electromagnetic induction in my lessons. So here we go. Stating words the two laws of magnetic induction. Well, the first one, Faraday's law. The EMF induced is proportional to the rate of change of flux linkage. Notice that it says proportional, it doesn't say equal to. The second law is Lenz's law and is the one that normally requires a bit of thought. Lenz's law tells us that the EMF induced acts to oppose the change that created it. A lot of my students find the wording hard for this, so maybe try and perhaps commit this to memory. Lenz's law, the EMF induced acts to oppose the change that created it. The next part of this question is one of the best questions I've seen in a long time, and is about an electromagnetic brake. And yes, these really do work. And the question asks us to explain how they work. How does this act as a brake? So let's have a go. So it says, explain, using the laws of induction, how the device acts as a brake. Let's have a think then. First part is that current in the coil up at the top there creates a magnetic field between its poles of this magnet. This much we know. This means that the part of the disc directly between those poles, say there, is going to experience a magnetic flux passing through it. And because of this, the disc is turning. As it turns, that means that that little area that had a flux finds that it's moved to a place where it doesn't have a flux. And because of that, it's experiencing a change in the flux passing through it. And this, of course, from Faraday's law means that there's going to be an EMF generated in that part of the disc. And Lenz's law tells us that this EMF will oppose the change that created it. Now, the change that created it was the rotation of the metal disc. And therefore, what we find is that within that little area of the disc, there's going to be an EMF which creates a current, which creates a magnetic field, which in this case pulls the wheel back in the opposite direction to which it was turning, i.e. braking the system. Now, the bit in the brackets there is not really necessary according to the mark scheme, but I just thought it was an interesting thing to say. And of course, as the piece of the wheel moves out from under the poles of the magnet, of course another bit comes up from behind to replace it. So this is a continuing process. What a great question. So in the last part of this tremendously brilliant question, we're asked to compare a conventional braking system with pads and the electromagnetic brake. So what's the disadvantage of the electromagnetic brake? Well, that's easy. Basically, there are no moving parts in it, so there's no friction, no wearing out of pads, no heat generated. A disadvantage of the electromagnetic braking system is based around the fact that the EMF is proportional to the rate of change of flux. This means that when the wheel is turning fast, we have a high rotational speed for the disc. That means we'll have a greater induced EMF and so a greater braking effect. In other words, when this wheel is turning slow, you're only going to get a small amount of braking. So perhaps the braking system is not much used for slow moving vehicles, like your bike.